All right, in this video, I'm going to debrief the activity about iPhone sales and the need to transform the data when it's nonlinear. All right, so let's take a closer look at this scatter plot. Now, this is the same one from a couple lessons ago. And before we had tried to fit a line to model this data, but a line isn't really the best fit. And you can see that when you use a line, you get these residuals, which tend to have a nonlinear pattern. Okay. And the reason for that nonlinear pattern is because the original relationship was nonlinear itself. Okay. So it doesn't make sense to try to use a linear model for a relationship that's nonlinear. And that's essentially the response to question number one. Okay, so the scatter plot and the residual plot both show a nonlinear pattern. Okay. All right. So thinking about functions we learned in algebra 2, pre-calculus, one of them was the exponential function. And we would use this for a behavior where growth is slow to begin with, but then builds rapidly later on, which would kind of make sense for the sales of a new product, right? In 2007, the iPhone was brand new, and so growth might have been slow at the beginning. Not a whole lot of people were, adopting these type of smartphones, but then it became very popular, and then sales just kind of blew up. Okay. So this really has all the makings of exponential growth. All right, so thinking back to algebra 2, this is the general form of an exponential function. Okay. So y equals a, which is some multiplier, some coefficient, times b raised to the x power. B is a base and x is an exponent. Okay. And then the inverse of exponents are logarithms. So for base 10, we have the common logarithm, and for base e, we have the natural logarithm. All right, so what I'd like to do at this point of our debrief is talk about how we can take this function, which is exponential, and manipulate it so that it becomes linear. Okay. I'm going to do this off to the side here. Okay, so y equals a times b to the x power. Okay. All right, so what we're going to do is we're going to use the inverse function to make this linear. All right, so we're going to take the logarithm of both sides. All right, so that'll be log y equals log of a times bx. And now we're going to use properties of logarithms. Okay, the logarithm of a product is just the sum of the individual logs. And so this will become log y equals log a plus log b to the x. A second property of logarithms is that the logarithm of a power is the exponent times the logarithm of the base. And so continuing to manipulate this equation, we're going to have log y equals log a plus x times the log of b. Okay. And we're going to make one last adjustment, which is we're going to reorder this product here. We're going to put the log b in the front of the product and x in the back of the product. So our final equation is log y equals log a plus log b times x. Okay. Now looking at this at first glance, it doesn't look like a linear function. Okay? But if you just consider the entire expression log y as the output, and then log a is just a number, right? A is just a number, it's a constant, so its logarithm is just a number as well. So this represents the constant or y-intercept of the model. And then log b is also a constant, but it's being multiplied by x, which makes it the slope. Okay. And then x, of course, is the input. Okay. So even though it's a little bit more complex looking, it has the structure of a linear function, right? And output equals a constant or y-intercept plus a coefficient, aka the slope, times an input value. Okay, so we essentially have a linear function now. Okay. All right, so this is a good time to pause the video, and then in your tables you're going to work on questions 3, 4, and 5. Okay, and then we'll debrief those questions and then do 6 and 7 together as a class. All right, so pause the video and then unpause when you get to question 6. All right, so you've worked on questions 3 through 6. Let's talk about it. So in question 3, you took the logarithm of the actual units sold, and then you created a new scatter plot. Okay. Now, something to notice is that we're recording the year as a single or 2-digit number now instead of a 4-digit number. And then hopefully you use the common logarithm, so that'd be log base 10 and not the natural logarithm, to get the last column of values. Sorry about that. All right, so we need to include a label here on the vertical axis. So what we want to label this is the log of the units sold. Okay. And when we look at the form now, it doesn't have that non-linear form anymore. It looks much straighter. Okay, and that's what taking the logarithm had the effect of, is just kind of straightening out the relationship. All right, so when you use Staplet to get the equation of the least squares regression line, Staplet is just going to write, y hat equals a plus bx. Okay. Staplet does not recognize that you took a logarithm, so it's just going to write a generic equation. Okay, but we know we took a logarithm, so technically this should be the log of y hat equals a plus bx. But of course, even better than writing the equation with just x and y, we should probably include context. So we could say the log of the units sold, predicted units sold, is negative 1.54 plus 0.18 times. Now we have to write year after 2000, since the year is being recorded as a single or double digit number, not a 4-digit number. Year after 2000. All right, so that's a much better way of writing the equation because it has context now. Okay, so question 5 gives you the residual plot and asks you to interpret it or analyze it. Notice that this residual plot looks very random. We have random scatter, which is very different from this residual plot, which had a clear curved pattern, clear nonlinear pattern here, and then random scatter here. So actually random scatter is a good sign. Okay? It means that the model that we fit accounted for all of the pattern and there's no pattern left over. All right, so let's do questions 6 and 7 together. And the reason why I want to do it together is because there's a lot of algebra, okay? And, even though this course is a math course, it's not meant to be very heavy on algebra. And so I just want to kind of support you with these two questions. So question 6, we want to predict how many iPhones would have been sold in 2015. All right, so we're going to begin with just writing the formula down. Okay. So the log of predicted units sold equals negative 1.54 plus 0.18 times the number of years after 2000. Well, if we're trying to predict for 2015, that would be 15 years after the year 2000. So we're going to substitute 15. All right. Now I'm just going to use my calculator to simplify the right-hand side. Okay. And it comes out to about 1.16. Okay. So the log of the predicted units sold is 1.16. Okay. Now, that's great, but it's not very useful because people don't sit at shareholder meetings and talk about the log number of units sold for iPhone. They just want to know how many units are sold. Okay, so we need to undo the logarithm. Okay. So here's where the algebra is going to come in handy. So to undo a logarithm, a common logarithm, we need to use the common base, which is base 10. So we're going to do 10 raised to the on the left side and on the right side. So base 10 cancels the common logarithm. And so now we're going to have predicted units sold equals 10 raised to the 1.16, which is approximately 14.45. Okay. And that is the actual prediction that we want. There's 14.45 million iPhones, okay, predicted to be sold in the year 2015. All right, question 7. Calculate and interpret the residual for this year. So a residual is the actual amount minus the predicted amount. Okay. Now the actual amount, we have to go back to the table, right? So the middle column has the actual amounts. The year was 2015, so 13 million iPhones were actually sold that year. Our model was predicting 14.45. That's a difference of negative 1.45 million iPhones. So calculation is done, but we still need to interpret it. I'm just going to borrow the sentence frame from, one or two classes ago. So we want to say something like, the actual Y value with context is residual units above or below the model's prediction when X is equal to a certain number. All right, so that's the generic sentence frame, and now we'll fill in the keywords. The actual units sold, or iPhone units sold, is 1.45 million below. The reason why we're using below is because the residual is negative. Below the model's prediction when the year is 2015. All right. So, last page. Okay, formal notes. So this activity introduced you to one scenario where the relationship was nonlinear. We did a transformation, which effectively made it look more linear, and then we fed a model to the transform data. Now there's 3 main transformations that we're going to do in AP Stats. So first, if you make a scatter plot and it already looks pretty linear, you don't need to transform anything, right? You're just going to continue to plot the X values versus the Y values. If you create a scatter plot which has the traits of an exponential function, that's what we did in the activity today, right? This has the makings of an exponential growth. Okay, what you're going to do in that case is you're going to transform the Y values. So instead of plotting X versus Y, you'll plot X versus the log of the Y values. Okay. And when you plot the transform data, it should look more linear than the original data. The third type of function or form that you might see is that of a power. So something that's a polynomial, so quadratic, cubic, or higher degree polynomial. If your scatter plot has a polynomial form, then what you're going to want to do is transform both variables. So you're going to plot the log of the x values versus the log of the y values. Okay. Now, whether you take the common log or the natural log doesn't really matter. Okay. I think in this activity, I'm just writing log, which refers to the common log base 10. All right, so you transform the data, you replot the transformed data, hopefully it looks more linear, and then you build your model. Okay. But when you use your model to make predictions, there's a lot more algebra involved because now you're dealing with logarithms. So when we talk about predictions, you're going to plug in your input, your x value, okay, do some simplifying or evaluating, but then you still have to solve for y. And when you're solving for y, you might have to undo a root, you might have to undo a logarithm in order to isolate the variable y. Okay, looking back here at question 6, we had to undo this logarithm by using base 10. Okay. All right, so as examples here, if we had this equation log y, this really should be log predicted y, equals a plus bx. So first of all, we plug in some number for x, our input, simplify the right-hand side, and then we'd have log of y hat equals some number. And then we can use base 10 on both sides to cancel the log and get predicted y equals 10 raised to whatever number we had. Okay. And this would work for natural log. So let's say our model was the natural log of predicted y equals a plus bx, right? We would still plug in an input value for x. Okay, so then we'd have natural log of y hat equals some number. But this time we would use the natural base, so base e, and raise both sides to that base. Okay. So base e cancels the natural logarithm, and we would be left with y hat equals e raised to some number. All right, just to give you one more example, suppose we built a model that was y cubed equals a plus bx. Okay, how would you get the prediction now? Well, you'd plug in your input for x and then evaluate the right-hand side. So you'd get y cubed equals some number. And then at this point you have to undo the cube, which would require taking a cube root on both sides. Sorry, there should have been hats on those y's. All right, so now y hat equals the cube root of whatever number you had previously. All right, we talked about it in the last activity, but good models have the following three things. Okay, they're going to have a low S statistic. Okay, S is the standard deviation of the residuals, which represents the typical prediction error. We want that typical prediction error to be low. Secondly, they're going to have a high R squared statistic. Okay. R squared is called the coefficient of determination. That name's not important. It measures the percent of variability in the y values explained by the model. We want a high percentage of that variability to be explained by our model. So we want high R squared values. Lastly, good models are going to have residual plots with no leftover pattern. Okay. Because we want the model to explain away most of the pattern, so what's left over, residual means left over, what's in the leftovers is no pattern at all. Okay. So like this is a good residual plot. It has no pattern in it. The one on page 1 is not a good residual plot. it shows a curved pattern, which indicates that there's still that curved pattern in the data set. All right, now I hope that you landed in a good spot in this activity. If there's still time remaining in the period, I'd love for you to take a look at the application problem with your table. Also, don't forget there was an application problem from the first activity, and I really wanted you to do part C of that one so that you get practice using those formulas. All right, I hope I see everybody on Wednesday. Fingers crossed.